Hey guys, this video is over an introduction to mechanisms in the kinetics unit. Alright, so reaction mechanisms are the different steps that a reaction goes through while it's taking place. Alright, so if this right here is our reaction, right, we have nitrogen dioxide reacting with carbon monoxide to produce nitrogen monoxide and carbon dioxide. That reaction doesn't really occur the way that it's written. Okay, this is one of the suggested mechanisms for that reaction. So it has two steps, all right, and these steps are called elementary reactions. So elementary reactions are just the steps that take place within an overall chemical reaction. Elementary reactions are not reactions themselves. Most of the time, an elementary reaction will not produce a stable intermediate, a stable molecule that will last longer than a couple of seconds in a reaction, so it's not really a full reaction. That's why we call them elementary reactions. Okay, so they take place in steps. And so this would be a two-step mechanism. Like I said, elementary reactions can form intermediates, and intermediates are formed by an elementary step and then they're consumed in a subsequent step. So like right here, we have nitrogen trioxide made, and nitrogen trioxide is consumed right here. So it's made by one step and then consumed in a subsequent step. And as you can tell, it's not in our overall reaction at all. And so just to prove to you that that is the overall reaction, I'm going to go ahead and add these two steps together. All right. So if I add these two steps together, then what I notice is that nitrogen trioxide, the intermediate, would actually cancel out. So it's an intermediate is produced by one step and then consumed by a later step. All right. And then one of the nitrogen dioxides would actually cancel out as well. So then when I add everything together, everything on the left side of the arrows of the yield arrow, I have nitrogen dioxide gas plus carbon monoxide gas makes nitrogen monoxide gas plus carbon dioxide gas. All right, and so that is the same thing that we have up here at the top where I had pointed out earlier. All right, and why the rate law is written here is important, and we'll see that later. And I also wanted to show you guys a reaction profile for a two-step mechanism because I think it's important that you see it now instead of later. As you can see, it's got two peaks instead of one normal one. All right, and what that means is that you've got two steps. This is the first step, and this is the second step. And so right here at the dip, right in the middle, right here, that's where the intermediate is formed. Okay, so that's where these this intermediate is formed. That's where we would show it on a reaction profile if we needed to. All right. Now we have the energy of activation for the first step, and then we have a small energy of activation for the second step, and that will come into place here in a little bit. Here's the reactants for our overall reaction, and here are our products, just like normal. All right, so you would still find the delta H of the reaction by going from where the reactant started to where the products finished. All right, okay. Molecularity is the number of reacting species in an elementary step. So that's a key word here. You can't have molecularity for a reaction, but only for the steps in the mechanism. Okay, and just to give you peace of mind, I'm never going to make you write a mechanism. You'll just have to prove whether or not a mechanism is valid. Okay, and it's pretty easy. All right, so rate laws for the elementary steps can be directly written from its molecularity. You just use the coefficient as the order for that reactant. All right, so if you only have one reactant, then it's called unimolecular, and you can write the rate law directly from that. All right, so since there's a 1 here, right, then this would be raised to the 1, and it would be first order with respect to A for that elementary step. All right, if you have two reactants, so either they're both the same thing, or you have an A and a B, those would both be bimolecular because we have two reactants. So it's bimolecular, like bicycle has two wheels. All right, and so it would be A squared for this one, or it'd be A to the first, B to the first, because those are their coefficients, right? And that would still be second order overall. All right, and then the last one is termolecular, and termolecular is really weird because they're very, very unlikely to occur. But it's when you have 3 reactants, and so overall you're going to get 3 would be your overall order. All right, and so I even put over here that they're very unlikely. So if you were to get a termolecular elementary step, you might want to go back and double check your work because they're unlikely that 3 things are going to hit each other with the right orientation for the reaction to occur. All right, so if this is our elementary reaction and we wanted to write the molecularity for it, then I would just write that it's bimolecular because I have 2 reactants, right? I have O3 and NO, so it's bimolecular. And then it would be rate is equal to K times the concentration of O3 times the concentration of NO, and both of those are to the first power. And so it's bimolecular because it's second order for that elementary reaction or elementary step. It is not a complete reaction. All right, write the rate law and determine the molecularity for the following elementary reactions. So just like we did before, if I was to write the rate law for the first one here, rate is equal to K times the concentration of CH3NC. And it is going to be unimolecular because there's only one thing there. All right, so there's only one of these, and so this is to the first power, and it's unimolecular. In B, the rate is equal to K times the concentration of O3 to the first power. It is also unimolecular. Okay, and then C, we have O3 and oxygen atom reacting, and so this is bimolecular. So we have 2 reacting species. So each one is to the first power. The overall order is 2 for that elementary step, and so it's bimolecular. So there's one of these and one of those. All right, so the rate determining step is the slowest step in the reaction. The rate law is based off of that step only. If it's the slowest step, then that means that the rate seen for that reaction will depend upon that step only. So if we look at the mechanism that was written for the very first slide, we see this one. And if I wanted to write the overall reaction, then I would just add these together. So looking at it, I see NO3 here and NO3 here, and so they cancel out because they're on opposite sides of the yield arrow. Also, one of the NO2s would cancel out. And so what we end up with is NO2 plus CO goes to NO plus CO2. And so this would be my overall reaction. All right, and if you look over here at this picture that I found, it really shows good rate determining steps. So if these are 3 different steps, 1, 2, 3, the rate determining step for how fast we can fill this Erlenmeyer flask with the water is determined right here because it's backed up in here. And so it can flow right through the other 2 steps, but it can't, it has to wait until it can get through this cone. So that would be the rate determining step. So in this second one, the rate determining step would be step 2 because that's where everything gets backed up. So if this one is slower than this one for this mechanism, then that means it determines the rate, and our rate law can be written off of that. All right, and then of course in the third one, the rate determining step is the third step. So then looking at what we did before, where we write the rate law based on the step, we can write the rate law for that very first step, this one right here, right? Rate would be equal to K, and we'd have NO2 times NO2, because the only time that second NO2 cancels out is when we add it to the second step. Okay, so it's still there for this first step. And so we would end up getting rate is equal to K NO2 squared, which is what I've got written right here. All right, we do not consider the fast step at all when we look at how to write the rate law from the mechanism. All right, and this also tells us which step is going to be the rate determining step because the energy of activation here is so much larger than it is for the second step. All right, and that tells us right there that the first step takes longer. If the second step would have a bigger hump, then it would be the second step that determines the rate. All right, so valid mechanism. A mechanism can never be proven, not proved, maybe proved, Can never be proven absolutely. We can only say that it supports the reaction and it could possibly be a way the reaction occurs. So for a reaction mechanism to be considered valid, it has to satisfy these two requirements. The elementary steps have to add together to get the overall reaction. So you have to get the overall reaction when you add all the steps together. And the mechanism has to agree with the experimentally determined rate law. So we found out how to do that before, where you vary the initial concentrations and you hold some of the concentrations constant to see how the rate is affected. Well, the mechanism has to agree with that experimentally determined rate law. All right, so if we look at this one, write the rate law expected for this mechanism, what is the overall balanced equation for the reaction, and what are the intermediates in the proposed mechanism. So if I add them all together to get the overall reaction first, all right, then what I can see canceling out, C4H9 plus cancels out, right? C4H9OH2 plus cancels out, and then that's it. So now I'm going to write down what I've got. I've got C4H9Br plus 2 waters, because there's one here and one here. They don't cancel because they're on the same side. And then I'm going to get, oh, that's it for reactants. And then I'm going to get bromide, C4H9OH, and then H3O plus. So that's my overall reaction. You need to check to make sure that it's balanced, but this one is. It's good. And then it says write the rate law. So the rate law is always going to be based off the slow step. And so the rate is going to be equal to K, and we only have one reactant here. So it's going to be based on the concentration of that reactant only, because this is our slow step. And it has to tell you that it's slow. You can't know which one is slow unless they give you some piece of information that tells you that. And then the intermediates are going to be the ones that we canceled out here, because they were produced by one step and then consumed in a subsequent step, right? So right here, this one is produced and then it's consumed immediately later. And this one is produced and then it's consumed later. And so both of those are intermediates. All right, example number 2, I have the balanced equation, it's right here, and the experimentally determined rate law is shown right here. So it just wants to know if this is an acceptable mechanism, and usually you have to justify your response. So we're going to justify it. So if I was to write a mechanism from the slow step here, it would look like this. Rate is equal to K times NO2 times F2. And they're both to the first power because they both have one right here, and this is the slow step. It's based off that, those two reactants. Guys, they're not added in the rate law. It's the same kind of rate law we've always written. They're multiplied here. All right, so the slow step gives you the correct mechanism. Okay, it's right here, right here. And then if I was to add these two together, I'm just going to erase this. If I was to add these two together to get the overall reaction, then F cancels out, and I end up getting 2 NO2s plus F2 goes to 2 NO2Fs. And I have to check to make sure that's the right equation. Yes, it's the same here as it is there, so that should be good. All right, so catalysts, the way that they work, they speed up the rate of the reaction without being consumed by the reaction. So if we look at how they do that, they lower the energy of activation. So if this is the catalyzed pathway, the orange one, right, is the catalyzed pathway, and then the blue one is the uncatalyzed pathway. Okay, so I'm going to look at the catalyzed pathway with a red pen, and I'll use green for the uncatalyzed. So uncatalyzed pathway, we have a much larger energy of activation. And then for the catalyzed pathway, it's much lower, it's much smaller. So it lowered the energy of activation. Now remember, this is going to be for a one-step mechanism. And the way that catalysts work is they actually change the mechanism completely so that the energy of activation is lower. So like with this one over here on the right side, I have the uncatalyzed pathway has a very large energy of activation. And then for the catalyzed reaction, it actually changed it to a two-step mechanism, but it has a much, much smaller energy of activation. Right? Because the first step is really where the energy of activation is, because it's a larger hump. Right? So this is the slower step of that catalyzed reaction. slower step. Well, this one is faster because it's lower. All right, so this would be the rate determining step in that reaction. All right, so one mechanism for the destruction of ozone in the upper atmosphere is given. So we're given the overall reaction here. And if we wanted to know which species was the catalyst, a catalyst is something you've added. So it has to be a reactant before it's a product. All right, so if I look over here in the mechanism, this is a reactant before it's a product. So that would be our catalyst, nitrogen monoxide. All right, and then it says which species is an intermediate. Well, the intermediate is going to be a product before it's a reaction. It's going to be a product before it's a reactant. So this is a product before it's a reactant in the steps. So this right here, NO2, is going to be an intermediate. All right, and so for the uncatalyzed reaction, the energy of activation is 14 kilojoules. And would the catalyzed pathway have an energy of activation greater than or less than? And it would definitely be less than, because that's what catalysts do. They lower the energy of activation. So we'll do a few of these in class. It's really not that hard. It's just getting used to seeing it this way. If you can get mechanisms down now, it will really, really help you if you have to take organic chemistry.